to give the tolerance for the upper limit and lower limit. In this case, it is bilateral unequal, that is unequal tolerance on the upper side and tolerance on the lower side, plus 0.2 and minus 0.4. If we are finding the upper and lower limits using these, we will get the same limits as over here. 8.4 plus 0.2 is 8.6, 8.4 minus 0.4 is 8.0. Other ways of writing the same thing in a different manner are unilateral positive, unilateral negative, when we want the nominal dimension to be different.
First, we will understand the concept of tolerance, why is tolerance needed, and what are variations on manufactured parts. So any part which you manufacture based on a process will not be perfect in its shape, size or form. Let's say you have a block and you're designing the block to be 10 mm dimension in width. So this is the design dimension, which is 10 mm, also called as the nominal dimension, and then you take it for manufacturing. So the block is manufactured. Consider this to be the block which is coming out after manufacturing as produced part, and then you measure it with a vernier caliper. You measure the width. You will find that width of that block will never be perfectly 10. It will always be away from the nominal dimension, or it will always be different for each and every part. One will be 10.2, another one will be 9.8, another one will be 9.9. So there will be a certain range of variations which will occur on that design dimension, and hence we will have to specify that design dimension along with a certain range. So that range over here is 10 plus or minus 0.5, and that range is nothing but the tolerance. So when we specify this dimension on a drawing, we always need to attach a tolerance with it. So this tolerance is the range of deviation allowed from the nominal dimension or the specification of a design. That means that through this denotation, the designer is saying that if the dimension of this block, the width is 10.5, it is still okay for the design, but it is not the optimal. The optimal is 10. So if it is 9.5 or if it is 10.5, then it is still acceptable for the design, but it is not the best case. So this tolerance range has to be specified by the designer either explicitly or implicitly to establish the functional limits for the variations of the part dimensions or features. So basically this limit says that if this part when manufactured goes beyond this limit, that is if it goes beyond 10.5, then there will be issues with the function, or worst case there will be a case in which the part does not assemble itself along with the assembly. So any dimensions of features, any specification of features, any orientation of features, or any size of features has to be associated along with the variation which is acceptable on it, which is nothing but tolerance. And that says that within these limits, the part will function as intended. Hence, in mechanical design, such that the part will perform its function as intended, these variations have to be specified explicitly or implicitly in the engineering drawing, so that the communication is clear from the design to the manufacturing as to what the limits of variations of each and every part and each and every dimension are. Along with the concept of tolerance, it is important to understand the concept of accuracy and precision. So when parts are manufactured, they are manufactured through certain processes. So these processes can be anything from casting, forging, machining, molding, or sheet metal forming. And hence the tolerance range which you can attain for a certain design dimension will be dependent on that manufacturing process or on that specific operation which takes place to arrive at that final part. So some processes can manufacture to fine tolerances, that is very small tolerance ranges, and some processes will manufacture to larger tolerance ranges. Any process is generally evaluated through its precision and accuracy. So we will understand what is the difference between these two terms. Precision is how much the process can maintain the same output or manufacture a part at the same exact dimensions in a repeatable manner. So how much can the process maintain that same output, repeatability, that is precision. Accuracy is how much the process can maintain its output close to the required specification or the required nominal dimension. So let's understand the concept of accuracy and precision with the help of a dartboard game. So let's say if you want to hit the dartboard at the bullseye each and every time for 7 attempts. The first time you do it, you get the result like this. So all of the 7 tries have landed in a different place and they are nowhere close to the bullseye. It means that the result is neither precise nor is it accurate. Second attempt, you hit very close to the bullseye and all of these 7 attempts or 7 darts are lying very close to each other. This would mean that the result is highly precise and it is also accurate. You have another go at it. In the third attempt, you find the result as shown. All of the 7 darts are lying very close nearby to each other, but they are not lying near to the bullseye. This means that the result is highly precise, but it is not accurate. This same concept can be applied for manufacturing process, and let's take the same example as we have already seen for a block which is having a width specification of 10 plus or minus 0.5. So if we are making 5 parts and we are measuring this width for all those 5 parts, and if you are getting the data as shown over here in this first case, 9.65, 10.2, 10.5, 9.5, 9.7, it means that it is not accurate and also it is not precise, because none of these data are very close to 10 and also all of the data are scattered. So the process can be said as it is not accurate and not precise. In the second case, we get this set of data 9.65, 9.62, 9.63, 9.65, 9.68. It signals to us that the process is able to give out the same input continuously, but it is not able to maintain the accuracy. So it is precise but not accurate. And in the final case, the process is accurate as well as it is precise. An important point to note over here is a process which is not precise cannot be accurate for its full range of data. It can have 1 or 2 accurate values, but if the process is not precise, then we cannot say that it is accurate also. So when we apply tolerance to a design dimension, we get 2 limits. One is the upper specification limit and one is the lower specification limit. So in this case, 10 plus or minus 0.5, the upper specification limit is 10.5, lower specification limit is 9.5, and the tolerance band or the tolerance range over here is 1 mm, which is nothing but this plus or minus 0.5, that is 0.5 up, 0.5 down. Total tolerance band is 1 mm. Now let's have a look at general tolerance ranges with regard to processes which are commonly used in manufacturing and production. So one such process is casting. So casting is not a high precision process, which basically means that the tolerance ranges which are attained for dimensions of parts which are manufactured by castings is in the range of 1 plus mm. So for example, if you are making a part using casting which is having a dimension, the design dimension is 50, so the minimum tolerance range which you can apply for the dimension is plus or minus 1 mm. So you cannot go below that because the capability of process is such. It is not a high precision process. It cannot maintain high levels of precision during the processing of the material. Another common process is forging, which is a bulk deformation process, and it generally has the tolerance ranges in 0.5 to 1 plus mm. So slightly better than casting, but not much better in terms of precision. Of course, there are many different variants of casting and forging also. Under casting, there can be die casting, which can be much better than sand casting. Under forging, there can be die forging also. There can be many different types of forging, which can have slightly better or worse precision as compared to other types. So since there are so many different types of processes, all have their own characteristics and all have their own tolerance ranges which are associated with them. The next process is sheet metal forming, which is also one of the most widely used process for different types of applications in different industries. So it is a highly versatile process which can have tolerance ranges ranging from 0.1 all the way to 1 plus mm depending on the specific application. Then machining, which is the most common manufacturing operation used in production, it can have a range from 0.01 to 1 mm. So there can be different levels of machining operations, from turning, facing, from coarse operations to fine operations, and then to finishing operations like grinding, super finishing, lapping. All of those can have very fine tolerance ranges in micrometers. Plastic injection molding is another mass manufacturing process which is very commonly used for making plastic parts. So it can have tolerance ranges from 0.1 to 1 mm depending on the precision as well as the size of the products which are being manufactured. So there can be hundreds of different varieties of processes and operations which are relating to manufacturing, and all of these can have a wide range of tolerances associated with them. So the ranges can vary widely. This will give you a basic relative differences between the most common processes. So understanding of these tolerance ranges of each process and each operation is very important for a design engineer who is deciding the specifications on the drawing. Many a time these tolerance ranges for specific operations, for specific dimensions may not be available for the design engineer. So we need to have some standard tolerance ranges for specific dimensions for specific processes, and hence that's why standards have been set, tolerance grades have been set for various applications. So why is tolerancing important in mechanical design from the performance perspective, or what is the functional importance of tolerancing in mechanical design? We will understand this with an example. We will take the very simple example of a pivot joint in a hinge. So a hinge is having a pivot joint, also called as a pin joint, which is allowing rotation about one axis. So this is the pin and this is the hole through which it goes. There are two brackets over here. One rotates with respect to the other. So that's a pivot joint. So if we take a section over here, we will get that the pin is having a certain size, and that is a certain size of a hole. And this gap between the pin and the hole is detrimental to the function of the pivot or function of the joint. So if we are manufacturing this hinge joint, and if we are finding this X value, that is the gap between the pin and the hole, and if in one sample the gap is very small, that is the X is very small, the hinge will be too tight and there are chances that the hinge will get stuck and there will be a compromise in function. On the other hand, if the gap is high, if X is high, that it will be too loose and there can be rattling, or there can be disorientation of the whole hinge joint. So again the function will be compromised. So the X has to be maintained at a specific value, and hence the tolerancing between the pin and the hole is very important for a hinge joint. So the tolerance specifications of pin and hole play a very big role in its reliability, the reliability of the hinge joint. The tolerances basically define the fit which takes place, which is basically the interface between the pin and the hole, which we will have a detailed look in the coming sections. Now we will have a brief look at the factors which play a role in specifying a tolerance for a certain dimension. So if you are a design engineer and if you are designing parts, and if you have to decide what would be the tolerance range for a certain dimension, for a certain feature, what would be the factors which we need to consider? We will have a brief look at that. So the first factor is the precision required for the application. There can be applications which require very high precision, require very close tolerances, that is the tolerance range is very small, like in micrometers, or there can be applications which require very open tolerances. So tolerance range can be in the range of 1 mm, 2 mm, especially in the case of castings. So depending on the application, these precision ranges can vary. For example, if we are designing machines which are required for measurements or inspection, then you would need to have very fine tolerances which are maybe to the level of gauge tolerance. So depending on the application, this precision will change and the tolerance levels also will change. Second is functional importance. So in a mechanical design, there can be many different features, many different parts which have different functional importance. Some parts are more functional important compared to others, and hence those dimensions or those critical dimensions have to be toleranced in a very careful manner. So functional importance is a very important factor in specifying a tolerance. Especially when it comes to interfaces in mechanical design, the tolerances can be of very high functional importance, as we have already seen from the example of the hinge. Also, if we take the example of a shaft in a rotating machinery and a bearing which is being installed on it, so that fit would generally be an interference fit which would require the bearing to be fastened onto the shaft. In that case, the tolerancing system between the shaft and the bearing is of utmost importance. Next point is costs associated with manufacturing. Let's say if we are manufacturing a shaft with a turning operation. So if we are doing coarse turning, then we would have open tolerances, that is the tolerance range would be larger. But if we are doing additional operation of fine turning and then grinding, then the cost required for manufacturing that shaft will be higher, but the tolerance range which we can maintain will be much smaller. And so it means that the finer the tolerance you want, the higher the cost will go for the manufacturing. The same is the case with all the other processes as well. The next point is process capability. As you have already seen, all the manufacturing processes have their limitations. Some manufacturing processes are versatile, some are not. So as we have already seen, the casting process cannot make parts which are having very fine tolerances. Hence, that has to be kept in mind while designing for those processes. And finally, assembly considerations. To make sure that assembly takes place between two parts, the tolerances, the locational tolerances, the orientational tolerances, the size tolerances have to be accounted for before specifying the tolerance for the mating feature dimension. So for an example, in machining operation, open tolerances are the liberal tolerances which are generally low cost and require a rough cut, like rough turning, rough facing. Closed tolerances or small tolerance bands which are finer require finishing operations like grinding, super finishing, lapping, which have very small tolerance bands. So we have already seen that tolerancing is a very important aspect of specifying the dimensions, specifying the characteristics of a certain part of a certain product. Now we will understand what are the sources of variations which contribute to a specific tolerance. So the CAD model, when we design the CAD model, that CAD model would represent the perfect geometry or the nominal geometry. And then we make the engineering drawing on which we specify the tolerances. So the tolerance is not only the physical variations which are occurring as a result of the manufacturing process, but are also a function of the discrepancies in measurement. This is an important point to note because as the manufacturing process is not 100% perfect, the same can be said about the inspection process also, the process which actually evaluates whether the part meets its specification or not, that is the inspection. So the variation in process can include tool wear. Let's say for example, if you are machining a part, if you are turning, and if you are using a cutting tool, that cutting tool, say after 1,000 number of pieces have been manufactured, will become worn out. And if we are using the same tool, then the dimensional variations will start to occur on the parts which are being manufactured, and hence that will affect the tolerances. Second, environmental conditions. Action of temperature, high temperatures, action of chemicals, corrosion, humidity, all of that will affect the output. Changes in equipment. Let's say a part has been manufactured on one machine and then that machine has to go for maintenance. Then you manufacture that same design on another machine. The result might be different because each and every machine will have its own characteristics and the variations might be different, and hence that will affect the tolerances. So changes in operator feed and craftsmanship level. Especially in processes which require high craftsmanship and high involvement of the operator, this can be detrimental. An operator with a lesser skill would lead to higher tolerances. That is, in case of variations, the variations would be high. but for an operator which is having high level of skill, the variations might be low and the accuracy and precision might be better. And finally, the method of assembly. So assembly sequences, assembly processes all matter a lot in terms of tolerances. Next would be the variations in inspection or the error which is caused during the inspection process. Now these variations may not be as high as variations in the process. The major contribution is of course because of the manufacturing process, but in some cases inspection variations have to be understood and studied such that there are no issues in the production. So one cause can be the changes in measuring equipment. So if there are changes in the measuring equipment from one equipment to the other, there can be different characteristics and which can lead to variations in the final output data. Unstable inspecting references can also be a problem, and that can give you unreliable data. So it is very important to have stable inspecting references, stable datums. Third would be wear on measurement equipment. So on continuous usage, wear and tear happens, and that will affect the accuracy of the measuring equipment. Then would be changes in operator. Similar to the process, some amount of skill is required for inspection, and the different levels of skill will also factor into the variations which are occurring or error. And finally, there can be errors like parallax error, which is basically the error in taking readings. So when the inspector is taking readings from a scale, that time parallax error can occur, or similar types of errors while taking observations. All of these will contribute to variations and hence will contribute to the tolerance on a specific dimension of a part. Now we will have a look at the different ways of denoting dimensions and tolerances on the engineering drawing. So one way of doing it is directly mentioning the limits. So the limits of the dimensions are shown over here, 8.6 and 8.0. 8.6 is the upper limit, 8.0 is the lower limit. There is no nominal dimension which is mentioned. If we are mentioning the nominal dimension, then we have to give the tolerance for the upper limit and lower limit. In this case, it is bilateral unequal, that is unequal tolerance on the upper side and tolerance on the lower side, plus 0.2 and minus 0.4. If we are finding the upper and lower limits using these, we will get the same limits as over here. 8.4 plus 0.2 is 8.6, 8.4 minus 0.4 is 8.0. Other ways of writing the same thing in a different manner are unilateral positive, unilateral negative, when we want the nominal dimension to be different. The most standard way of representing tolerances, however, is bilateral equal, that is having a nominal dimension and having an equally disposed tolerance in upper side and lower side. So 8.3 plus or minus 0.3. This is useful especially when we are analyzing the tolerances. When we analyze the tolerances, we generally want to convert all of the limits for specific dimensions into bilateral equal and then analyze them afterwards. So for the sake of analysis, we need to convert the limits into equal bilateral tolerances. So for that, a generic procedure is to find the limits, that is the limit values, upper specification limit and lower specification limit, find the difference between them, subtract them from each other, find the delta, then find the half of the difference, find the mean, and then write the specification in terms of equal bilateral tolerances. So mean plus or minus half of the difference. This would be the specification. We will have a look with one example. So let's say this is one dimension, this is one specification, 20 plus 0.5 minus 0.7. So the first step is to find the limits. So to find the limits, 20 plus 0.5 is 20.5, 20 minus 0.7 is 19.3. So 20.5 is the upper limit, 19.3 is the lower limit. Then we find the difference, 20.5 minus 19.3, that is 1.2. Then we find the half of the difference, which is 0.6. And then we find the average of the upper limit and lower limit, which is 20.5 plus 19.3 divided by 2. So this is the mean, that is the nominal dimension for equal bilateral tolerance. And then we write down the whole specification. So 19.9 plus or minus 0.6. So you can notice over here the nominal value has changed. Over here it is 20 and now it has changed to 19.9. Although the nominal value has changed from 20 to 19.9, the limits remain the same. So 19.9 plus 0.6 is still 20.5, 19.9 minus 0.6 is still 19.3.